All right, so the last time, the end of the lecture, we focused on pH. And we said pH is the negative log of the hydrogen ion concentration. Oh, come on, yeah, come on in, yeah. We could also write in terms of POH. POH is negative log of the hydroxide ion concentration. And then we talked about where did these come from. Well, they come from the equilibrium expression, Kw, which is the ion product constant of water, which is equal to the hydronium or hydrogen ion concentration. We're going to use hydrogen ion concentration for short, times the hydroxide ion concentration. And the ion product constant of water, again, equilibrium constant, at 25 degrees Celsius is 1.00 times 10 to the negative 14th. So we talked about that, and that this equation came out of the auto-ionization of water, that water will react with itself, which in shorthand we can write that as water breaks down to hydrogen ions and hydroxide ions. There's an equilibrium that's established here, and at equilibrium in pure water, the concentration of the hydrogen ion is 1.00 times 10 to the negative 7th molar, and the hydroxide ion concentration is 1.00 times 10 to the negative 7th molar. All right, so if we multiply these two numbers together, we get the ion product constant of water. And again, this is the basis for pH. You all know that the pH of something equal to 7, which actually represents negative log of the hydrogen ion concentration, which means that hydrogen ion concentration had to be 1.00 times 10 to the negative 7th molar. That's where we get pH. We assume in pure water, the hydrogen ion and the hydroxide ion are the same concentration at 1 times 10 to the negative 7th molar at 25 degrees Celsius. When we take the negative log of the hydrogen ion concentration, that's where we get the pH equal to 7. So another thing that we can do is let's look at the ion product concentration of water again. We can say that Kw equals the hydrogen ion concentration times the hydroxide ion concentration. And what I'm going to do this time is I'm going to multiply everything by the negative log. I'm going to use the negative log on each one of these terms. So over here I get negative log of Kw. And over here I get negative log of the hydrogen ion concentration. Now, when we take logs, we have two terms here we're multiplying. When we convert this to logarithmic form, what do we do to this multiplication? What does it become? Yeah, it comes the addition, right? So we would have plus the negative log of the hydroxide ion concentration. All right, so Kw we know is actually got a value at 25 degrees Celsius. It's 1.00 times 10 to the negative 14th. And we know that the negative log of the hydrogen ion concentration is pH. And we know the negative log of the hydroxide ion concentration is POH. And so what's the negative log of 1 times 10 to the negative 14th? 14. So here's another tool that you need to remember. 14 equals pH plus POH. Definitely need to know that. So that means if you know what the pH of something is, if you subtract it from 14, that will give you the POH. Or if you know the POH, you can subtract it from 14 and get the pH. So the tools for chapter 15 are these, this, and then you need to always keep in mind this equation here.
So far, when I look far in chapter 15, is the term POH actually used?
Yes, we use, they talk about it in terms of bases. There's a section on bases, but a lot of times, if we're working with basic solutions, we like to work with POH. If that is the active ion we're interested in how the hydroxide is going to react, ion is going to react with something else. We're generally interested in the POH more so than the pH. All right. I know pH is used the most. pH is definitely used the most throughout everyday life, but POH is also important to chemists as well.
If you're showing the different scales from what a base of 10 on the pH scale the same as a 4 on the pOH scale? Is it like
Yeah, right. That's right. So if the pH is 10, the pOH is 4. That's right, because it has to add up to 14. So on both scales, both the pH and pOH scale, the lower the value, the lower the number, the more acidic it is in pH, and the more basic it is in pOH. So if like you said, a pH of 10, you would say is what type of solution, acidic or basic? Basic, all right? So we could also say a pOH of 4, is that acidic or basic? It's basic. pOH of 4? Yeah. So they work interchangeably. Both of them work the same way. The lower the value of pH, the more acidic. The lower the value of pOH, the more basic. So if we're working in the realm of bases, we do use pOH quite often. But most of the time, what we've been working with in Chemistry 180 is acidic solutions, so we don't see pOH that much.
Wouldn't the higher the pOH make it more acidic?
Yeah, acidic. Yeah, the higher above 7, the higher the pH, the more acidic. But the lower the pOH, the more basic. Yeah. All right. Questions on these tools? All right. So these are the tools you definitely need to know. And this is, if you don't get these tools down, you're going to really struggle with Chapter 15, because I would say this is the main conceptual part of 15, is being able to apply these. All right. So then the next part is to apply these to everyday equations or to situations. So, let's do this. Is there anything up to 59 that you've looked at, something similar to this on Mastering Chemistry, or something in the back of the book you want to see worked out? If so, I'll work that out first. Otherwise, I'm going to jump into the more ice table type problems. All right, well, let's pick out a couple here, because I do want you to see a couple of things here. Let's first of all look at 43 on page 706. All right, 43 is a conceptual problem. And so if you understand the conceptual problem, we feel like you understand the concept. So in 43, we have 3 beakers labeled A, B, and C. All right? And in beaker 1, it says the 3 diagrams represent 3 different solutions of binary acid, HA. Water molecules have been omitted for clarity. So all the blue is the water molecules. They've been omitted for clarity. All right? The hydronium ions are represented by hydrogen ions, H positive. And that's what I say. We use hydronium and hydrogen ions interchangeably. In reality, it is hydronium in water, but a lot of times we just say H positive. Rank the acids in order of decreasing acid strength. All right? So, you see 3 different particles in these 3 beakers. You see red spheres by themselves. You see white spheres by themselves, and then you see red and white spheres bonded together. So which one represents HA? Yeah. All right, the red and white. So you know that is the unionized acid. It is stuck together, and then when it breaks apart, we say ionization has occurred, because we had HA. There were no ions in this substance. This is a nonmetal with another nonmetal. But then, when we add it to the water, it becomes hydrogen ions and the conjugate base, A negative. And these are aqueous. All right? So, out of those 3 beakers, which one is the strongest? A is the strongest. And why do you say it's the strongest? They're all ionized. Ionized. That's the term we want to use. All right. For bases, we'll say dissociated, because in a base like sodium hydroxide, these are ions to begin with. They are bonded together and it's neutral, and they break apart, and we get sodium ions plus hydroxide ions. So that's what dissociation means. Dissociation means breaking apart. ionization is dissociation that creates ions. So we say ionization for that. So we want to use the proper term. Ionization is when we start with something that is not in charge form and it becomes charge form. Dissociation, we're going from ions to ions. All right, so A is the strongest because it's completely ionized. What's the next strongest? B, because we do see in B there are, 3 molecules that are not ionized. And then what about C? Has to be the least because it has the most unionized acid. Okay? Next one I want you to be able to do is something like 45 or 46. This one, this 45 and 46 test you on, do you really understand the relationship between acid and conjugate base? And the relationship that as the acid gets stronger, the conjugate base gets weaker. All right? So if we're looking at this reaction we've already drawn, this is the acid. This is the conjugate base. And if we wrote this with the hydronium ion, this would be the conjugate acid. We could actually call it the conjugate acid here as well. But, again, when we're generally talking about acid-base pairs, we like to write it this way. We like to use the Bronsted-Lowry definition and draw it like this, where we can see and clearly identify the acid, the base, the conjugate acid, and the conjugate base. All right? So, in problem 45, on page 706, let's look at A. A, we have to see, this is the question, pick the stronger base from each pair. So we're doing the fluoride ion or the chloride ion. Which one of these is the stronger base? Which one? Okay, how many people think the fluorine? Raise your hand. How many people think the chlorine? Raise your hand. How many people don't know? All right? So here's what you have to do. You're going to take... Okay, let's look at the ions first. Huh? Are you sure for fluorine? Okay. All right, so let's look at these ions. Fluoride ion and chloride ion. Would you expect these substances to act as an acid or a base? Okay, let's have a vote here because I'm not hearing a good solid answer. How many people think these substances would act as an acid? How many people think they would act as a base? Oh, that's better. How many people don't know? There's a few. All right. Well, in order for it to be an acid, we would have to say what? It donates what? A hydrogen ion. Do these have hydrogen ions? No, so they're not acids. So they have to be bases. All right, so negative ions almost always are bases because they have the ability to accept a hydrogen ion and become neutral. So both of these substances have the ability to accept hydrogen ions and become neutral. But let's think about it. If the fluoride ion accepts a hydrogen ion, what does it become? If the fluoride ion accepts a hydrogen ion, what does it become? Hydrofluoric acid. All right? HF, hydrofluoric acid. If the chloride ion accepts a hydrogen ion, what does it become? Hydrochloric acid. All right? Now, let's talk about these two acids. Is one of these acids a strong acid? Which one? HCl. And what's the definition of a strong acid? Completely ionizes. That means it goes 100% this way. 100%. Means it's not going back. It's not going. Chloride ion will not accept a hydrogen ion and become hydrochloric acid. Because you said it was a strong acid, and the definition of a strong acid is it 100% ionizes. So chlorine, is it a strong base or a weak base? Very, very weak base. Chloride ion is not going to accept a hydrogen ion and become hydrochloric acid. Again, it would be a major concern if it did because, again, you'd be salting your food and the table salt, NaCl, would split apart into the two ions in water And the chloride ion would react with the water and form hydrochloric acid. We wouldn't want that. All right. What about HF? Strong acid or weak acid? Weak acid. So is it possible for the fluoride ion to accept the hydrogen ion and form this acid? Yeah. Most of this acid, we could guess and say maybe only 80% goes to these two ions. Maybe it's less than that. But 20% would definitely keep it in the molecular form. Now, I may have those flipped. It's probably more like 20% of, and let's do this. I would say, if I'm guessing here, I would guess this is more 20% ionized and 80% stays in the molecular form. So, yes, the fluoride ion will accept the hydrogen ion. It will form hydrofluoric acid because it's a weak acid, and weak acids want to stay in their molecular form. And so this reaction does happen, and so HF being a weaker acid, the fluoride ion is a stronger conjugate base, so this is a stronger base. This is almost a non-existent base, if anything. All right? All right, so let's look at B. Let's see if you're getting the hang of this. So in B, we have to compare the nitrite ion to the nitrate ion. So what you want to think about is what would be the conjugate acids of these two substances if they add it. So what we mean is if we add a hydrogen ion to these two substances, what are the conjugate acids? What's HNO2? Nitrous acid, strong acid, or weak acid? Weak acid. So HNO2 would be a weak acid. What about HNO3? Nitric acid, and it's a strong acid. All right? So this one is not going to accept the hydrogen ion because we said this is a strong acid. It goes 100% ionized. But this is a weak acid. So yes, it is possible for the nitrite ion to accept the hydrogen ion and become the nitrous acid. So yes, this is the stronger base.
If, like, for instance, like the HCl, if that won't ever go that way, how do you ever get HCl to begin with?
You have to do some other reaction. And I can't think of right off the top of my head of how we make hydrochloric acid, but it's a different, like I know how we make sulfuric acid. We have to bubble sulfur trioxide in water or do some type of reaction of sulfur trioxide with another acid to form that. So yeah, it's not a direct formation. All right. Now, here's the tricky one. Let's look at 45C. 45C, this is the harder one. So now we have the fluoride ion, and we're going to compare that to the, what's the ClO negative ion called? Do what? No. Yeah, you're right. Perchlorate is ClO4. What's ClO negative? Hypochlorite. See, this is why you got to know 170 before you come to 180, because we had that, right? Remember, it was hypochlorite with one oxygen, then chlorite, then chlorate, then perchlorate. That's why we have to know this for this. Because why is it so important? Because if I add a hydrogen to this and I get this acid, what's the name of that acid? It's hypochlorous acid. Hypochlorous acid. You know the ion is hypochlorite. Remember, ite ions make OUS acid. So that's how you're going to name this acid, by knowing the name of the polyatomic ion. And then, is this an oxyacid or a binary acid? It's an oxyacid. It's got oxygen in it. That's why we're building it from this polyatomic ion. That's another thing you got to know. Polyatomic ions, so that you know when you take this isn't called hydrochlorous acid. You don't use the word hydro in oxyacids. You only use it in binary acids. So this acid, what's the name of it? Hydrofluoric, because it's not an oxyacid, it's a binary acid. That's why the naming is so important. All right. So which one of these is this? So let's do this first. The hydrofluoric acid and the hypochlorous acid, are these strong acids or weak acids? They're both weak. They're both weak. So we got a dilemma here. The other ones, they gave us one that was weak and one that was strong, and we could easily figure that out. But now we have two weak acids. And you're going, well, how are we going to solve for this? So what do you think? What would you look for to solve this? Ka. Ka is important because Ka says that HF breaks apart into the hydrogen, or ionizes, I should say, into the hydrogen ion and the fluoride ion. And so the Ka for this, the expression would be the hydrogen ion concentration times the fluoride ion concentration over the molecular acid, hydrofluoric acid. And the hypochlorous acid would ionize, and again we should use double arrows here, and ionize into the hydrogen ion and the hypochlorite ion. If we write the Ka for that, then we would get the hydrogen ion times the hypochlorite ion over the molecular acid. All right, so Ka tells us what it tells us how strong the acid is, really, doesn't it? The higher the value of Ka, the more the reaction goes to the right, to the product, to completion. So we need to find the Kas for these two acids. So you have to go back in your chapter and look for a table in your book in order to solve this. So you start flipping backwards, and you see on page 667, you see a table of acids, their formulas, their structural formulas, ionization of the reaction, and then the Kas. So for hydrofluoric acid, is it not? It's there? Oh yeah, the third one down. 3.5 times 10 to the negative fourth. So I'll just write it here since we're running over. 3.5 times 10 to the negative fourth. All right, and the hypochlorous is 2.9 times 10 to the negative eighth. So which one's the stronger acid, hydrofluoric or the hypochlorous acid? Hydrofluoric is stronger because it has a larger Ka than the hypochlorous acid. So, which conjugate base is stronger? The fluoride ion or the hypochlorite ion? Hypochlorite is stronger. Hypochlorous acid is a weaker acid that makes the conjugate base stronger. So now we know if we have to choose on C, it's going to be the hypochlorous ion. Chloride ion, yeah. Yeah. You do not have to have them memorized. You will look at a table, they'll be given in the problem. There is a way to calculate them. If you know what the equilibrium, like the way that you would calculate these Kas, just like we did in the previous chapter, you would have to figure out what the hydrogen ion, the fluoride ion, and the molecular acid concentrations are at equilibrium. You would plug them into the expression, and you would be able to find the Ka. So you say, well, how is that going to happen? Well, if I give you the pH, you can tell me what the hydrogen ion and the fluoride concentrations are, because you assume that you had HF initially. You had 0 of this and 0 of this. If I give you the pH, you can use the inverse of the equation. We're running out of room. Let me put it right here. I could find the hydrogen ion concentration, which is equal to 10 raised to the negative pH. So if they give me the pH, I can plug it into this equation. I will get the hydrogen ion concentration, and we can assume then that the fluoride ion concentration would be what? Well, it'd be the same as the hydrogen ion concentration, right? If you start with HF and it breaks apart into hydrogen ion and fluoride ion, and you know what the hydrogen ion concentration is at equilibrium, you know what the fluoride ion is. Now you say, well, how would you figure out what the equilibrium concentration of the HF is? They had to give you the initial concentration of the HF, the hydrofluoric acid. So you take the initial concentration of the hydrofluoric acid, you would subtract off the equilibrium concentration, and that would tell you what the equilibrium, you would subtract off the change, and that would give you the equilibrium concentration of the hydrofluoric acid. And we may do a problem similar to that one. All right? All right, let's go on. Any questions on that? These problems take time. If you haven't started on the Mastering Chemistry, you'll need to start, because these problems, you can see, we've spent a half hour just doing really 2 problems here. So you have to take some time and work a little each. You're not going to sit down and do all this in two sittings. You have to do a little each day. Otherwise, you're going to get overwhelmed. All right. Let's go on to another more difficult problem. I don't know. I was thinking. I feel like we need to spend a little bit more time on. Well, let's do an easier one, then we'll go to a harder one. Let's look at problem number 55A. 55A. All right. So 55A, we have a 0.25 molar hydrochloric acid solution. And the question says they want you to determine the hydronium ion concentration, the hydroxide ion concentration, and the pH for this solution. All right? So the first thing you have to do when you're doing a problem like this, you have to identify the acid. Hydrochloric acid, is that a strong acid or a weak acid? Strong. So the next thing you would do, since they're asking for hydronium, let's write it like the Bronsted-Lowry definition. So we have hydrochloric acid reacting with water, forming the hydronium ion plus the chloride ion. And we could put a double arrow, but again, we know this reaction is pretty much irreversible, so we know it's really going 100% this way. So I don't know if you want to put that in there or not. You may want to just leave it like that, actually. All right. So you can do an ice table for this. You could say this is 0.25 molar. We're not worried about the water. Why? It's pure liquid. Concentration's constant as long as it's present. So we don't worry about that. This is initially 0. This is initially 0. How much of this unionized acid are we going to lose in the change? All of it is correct because it's a strong acid. We said 100%. So we lose this. That means we gain 0.25 molar of this. How much of the chloride ion do we gain? 0.25 molar. So at equilibrium, this is 0. This we don't worry about. This is 0.25 molar. This is 0.25 molar. All right. So tell me what the hydronium ion concentration is going to be. Yeah, close the door. It's fine. What is it? 0.25 molar, right? Right here it is. Here, here. There's my answer. Remember, brackets mean molar concentration. So you have determined the concentration of the hydronium ion for a strong acid. Now, a lot of you are looking at that going, I could have done that without doing all this. Absolutely. When you get the hang of this, as soon as you know it's a strong acid, whatever this concentration is, and it's monoprotic, you know what the hydronium ion concentration is immediately. You don't even have to do an ice table. But when you're first starting out, I think an ice table is important to see where you're going and you can see the mechanics of what you're actually doing. But yeah, when you do this on a quiz or test, you're going to say, 0.25 molar hydrochloric acid. I know it's a strong acid, 100% to completion, so therefore I know that the hydronium ion is 0.25. All right, now we got to find the hydroxide ion concentration. There's two ways to solve for this. Some of you will do it this way. You will say Kw equals the hydronium ion concentration times the hydroxide ion concentration. And you'll say, well, Kw is 1 times 10 to the negative 14. The hydronium concentration is 0.25 molar. And so the hydroxide ion concentration is, if I take 1 times 10 to the negative 14, I divide it by 0.25 molar, that will give me the hydroxide ion concentration. So let's do that. See what we get. 1 exponential negative 14 divided by 0.25. And you get 4 times 10. Oh, we should have been able to do that one in our head, right? Because 0.25 is 1/4. So we get 4 times 10 to the negative 14. So that's one way to do it. Now, here's the question. Is this solution acidic or basic? Well, I'm hearing two different answers. Let's have a vote. How many people think this solution is acidic? How many people think it's basic? How many people don't know? All right? So here's the question. Which concentration is in greater quantity? The hydronium ion concentration or the hydroxide ion concentration? Okay, here's the hydroxide ion concentration. Here's the hydronium ion concentration. Hydronium ion is higher in concentration, so therefore it's acidic. Now, even if you didn't know the hydronium ion concentration, if you saw a hydroxide ion concentration of 4 times 10 to the negative 14th, what does that tell you? It tells you there's very little hydroxide ion in this solution and mostly hydronium ion. All right? So even looking, again, in any aqueous system, it's a balance of hydronium and hydroxide. And these two values, when multiplied together, have to equal 1 times 10 to the negative 14th at 25 degrees Celsius. So if the hydroxide ion is 4 times 10 to the negative 14th, then the hydroxide has to be really high to get to 1 times 10 to the negative 14th. But when we multiply those together, right? Do you guys follow that or not? I mean, it has to be 0.25, right? 0.25 molar hydrochloric acid. That's 2.5 times 10 to the negative 1 in the hydrogen ion or the hydronium ion concentration. Much greater. All right, here's another way you can do this problem. You find the pH. So you say pH equals negative log of the concentration of the hydronium ion. So we do that first. So let's plug it in on your calculator. 0.25 log, change it. So you got 0.602, right? Actually, for significant figure purposes, it is really only 2 significant figures. We could carry an extra one right now, though. Somebody was asking, how do you know the significant figures? In a logarithm, like when I say a pH is 7.23, it's what's after the decimal reflects the significant figures in the number. The 7 out in front represents the power. So if I say 7.23, the hydrogen ion concentration had 2 significant figures in it before I took the negative log of it. So this only has 2. So there's a number out in front here, and then really only these 2 digits are significant. But we don't want to round off and have any round off there, so we'll carry it out to 0.602 right now. All right? So that's the pH. So here's the trick. You can say 14 minus 0.602, and that will give you the POH. All right? So you could do it this way. 14 minus 0.602. Get 13.39, we'll say 39. All right? Or 398, whatever you want to do. If you want to carry an extra significant figure, like 398, we'll do that. We'll carry an extra one for right now. All right, that's the POH. Then how do you convert that to the hydroxide ion concentration? Well, the hydroxide ion concentration would be equal to 10 raised to the negative POH. And you say, where'd that come from? Well, it came from when we said POH is equal to the negative log of the hydroxide ion concentration. Well, we could do the inverse of both sides. We take the negative sign, move it over here, and then we want to get rid of this log, so we take the inverse, so we would get the OH on this side, OH negative, the hydroxide ion, is equal to 10 raised to the negative POH. So you're going to take this number and raise it, make it negative, and so we're going to take that, make it negative, and then do the inverse of it. And we get 4 times 10 to the negative 14th again. So we get the same answer. And we should. All right? So it's up to you. You can do it one way or the other. For this one, this was probably the easiest way on the left, but some people like working, they don't want to work with, I don't know, some people like working with it on the right, so it's up to you. You can do it either way.
So you just do 10 to the negative POH?
Yeah, 10 to the negative POH. All right? So I guess the advantage of doing it this way, we did solve this answer, right? There's the pH. So in this problem here on the right, we solved for the pH and the hydroxide ion. Yeah.
I don't understand whatever you were saying, which one's more acidic or basic.
All right. So at equilibrium, this is the concentration of the hydroxide ion. At equilibrium, this is the concentration of the hydronium ion. All right? So if it was strictly neutral, it would be 1 times 10 to the negative 7th in hydroxide and 1 times 10 to the negative 7th in the hydronium ion. All right? Now, we see that the hydroxide ion is really low, 4 times 10 to the negative 14th, way down here. So as this goes down, the hydrogen ion has to go up so that when we multiply these together, we get 1 times 10 to the negative 14th, the ion product constant of water. So we know that 0.25 is a much larger number than 4 times 10 to the negative 14th. So knowing that, you know this is an acidic solution. The hydrogen ion is either way you want to say it, I use these interchangeably. The hydrogen ion or hydronium ion is dominating to much greater concentration than the hydroxide. All right? So you can look at POHs or pHs and be able to tell whether the solution is acidic or basic. Or hydroxide ion concentrations and hydrogen ion concentrations.
Plugging in where you see 10 to the negative POH, you're plugging in negative 13.398.
Yeah, this is the POH. So negative POH. Yeah. Are you putting in a 10 raised to the negative 13.398?
It gives me an error.
It's probably the way you're putting it in on the calculator. Yeah. Are you plugging it in as you see it? So you would say 10, and it'll say parenthesis. Then don't use the subtraction key. You have to use the plus minus key. And then put in 13.398. Yeah. Now that's a difference, right? On the calculator, you have function keys, addition, subtraction. Don't use the subtraction key as the negative key because it will give you an error. Because it's saying you're doing a logarithmic function of a function. So keep that straight. All right, let's go on. The next problem. I don't know which one I really want to do. Actually, I want to do 2, and then we'll come back and I want to do 2 harder. I want to do 2. It's more straightforward, and then we'll come back and do a harder, an easier one. I just find I really want to do 60 because it is a practical problem. This is the kind of problem we do. This is what Ray Ann does when she's trying to figure out. She goes like, I need to make 5 liters of a certain molarity hydrochloric acid solution, and this is the kind of problem she does. And I think it's important that you can make solutions, but that problem's not as easy. The concept's easy, but the calculation's a little harder. So let's look at problem number 73. Problem 73 on page 707. All right, so for 73, it says, 73 on page 707. Do what? All right, so let's look at this one. So it says a 0.148 molar solution of monoprotic acid has a percent ionization. That's why that ionization is so important. Of 1.55%. Determine the acid ionization constant. So here we're determining the equilibrium constant. It's kind of like what we were asking previously. Like sometimes do we find K? Yeah. In this one we're going to find K. All right, so the first thing to do any equilibrium problems, you've got to have a balanced chemical equation. So what's the equation going to look like for this reaction? HA. So I find some students struggle with that. If it says a monoprotic acid, this is a monoprotic acid. If they said that you're dealing with a diprotic acid, the general form of a diprotic acid would be H2A. Or if they say a triprotic, you would say H3A. So they say monoprotic. So we say HA, and that ionizes into the hydrogen ion plus the conjugate base, A negative. And we would make a double arrow, because we're talking about equilibrium here. All right? And we know we're talking about a weak acid here. And how do we know we're talking about a weak acid? Yeah, the percent ionization tells you. If it's a strong acid, it'd be 100% ionized. But this is 1.55%. All right. So we take the original concentration of the acid, 0.148 molar. What's the initial concentration of the hydrogen ion in the conjugate base? 0. Now, I will say this, about the original concentration of the acid. And I don't know if there's a problem like this in your master in chemistry. I tried to avoid it. I don't think it's in there. But in pure water, if we have a really, really weak acid, the hydrogen ion becomes important in just pure water, right? In pure water, the hydrogen ion concentration is 1 times 10 to the negative 7. So sometimes that affects the actual pH. You've got to be careful there. But for most of these problems, yes, the molecular acid is going to dominate the pH. That's why your book, when you're looking in the book and they're doing these ice tables and they have this approximate 0 for the hydrogen ion, that's what they're saying. They are saying that we assume it's 0 because even in pure water it's 1 times 10 to the negative 7. But for really, really low concentration of acids, it can become a factor. All right, how much of the HA are we going to lose? Yeah, 1.55%. That's what ionization means, right? That's why you got to get the terminology down. When they say 1.55% ionized, they're telling you how much of the HA is being converted. So how are we going to find that? You're going to take 1.55 divided by 100. That's what it is as a percent. And you're going to multiply that by what? Concentration of the acid initially. All right. So when we do that, 1.55 divided by 100 times 0.1. All right. So you got 2.294 times 10 to the negative 3. And what's your units? Molarity, moles per liter. All right. So keep that in mind. All right. So that's the percent ionized. So that's what you're going to subtract here. You're going to subtract from 0.148, and you may want to write it here. If you're going to do it that way, you may want to write it out in expanded notation like that. Okay, how much hydrogen ion are we going to gain? That's right. Since the stoichiometry is all 1 to 1 to 1, we're going to gain 0.002294 of this. How much of the conjugate base are we gaining? Same amount. All right. So equilibrium, this is 0.002294. This is 0.002294 for the conjugate base. And we're going to subtract this number from 0.148. And we get 0.1457. We'll carry an extra significant figure for right now. All right, so here's your ice table that we've been doing in chapter 14 and now 15. It's that important. That's why I said it's a tool. All right, so the other thing you need to have here, which we probably jumped the gun on, we need to have the expression. Ka for this is equal to the hydrogen ion concentration, and we know it's aqueous, so we should put those in there. We know aqueous has to be in the expression, and then the undissociated acid, which is also aqueous, in the denominator. Yeah.
Is there a reaction factor involved in these types of equations?
We mean a reaction factor.
Huge. Where's that
Yeah, there's a Q. There's always Q. There is always Q. It's just that we already jump here, all right? We know Q is what? Is it greater than K or less than K? It's less than K. Why do we know it's less than K? Yeah, well, we know that there's no product to begin with, so Q is equal to 0. So we know Q is equal to 0, Q is less than K. We got to go forward. So that's an assumption, and I think students get it really fixed on it, like you just automatically know it's going. I did. I said we're automatically going in the forward direction. But in reality, if we slow it down, we know it's going in the forward direction because there's no product to begin with, and we know Q is going to be less than K because Q is equal to 0. So if this problem, and if we have time, we will do a problem where we have something on the product side. If there is some on the product side, we have to calculate Q to determine which way the reaction is going to go. This one we know is going to the right to the product. All right, so what we have now, we don't know what Ka is. That's what the question asked to solve. For the hydrogen ion concentration, we have 0.002294 at equilibrium. I'm going to drop the units since the units are meaningless for the acid ionization constant. All right, same concentration for the conjugate base. That makes sense. You got HA, it breaks apart. There's a hydrogen. There's a conjugate base. Hydrogen ion and conjugate base. All right, and then in the denominator, we're going to put the 0.1457. All right, so when we calculate this out, we will get the Ka for this reaction. So if I was doing this, I would probably just take this 0.002294, I'd square that and divide it by 0.1457, and I get for an answer 3 point. Now here's where we want to watch our significant figures. Let's do a rough answer first. We'll say 3.612 times 10 to the negative fifth, is it? All right. All right, how many significant figures should we have in our final answer?
3.
All right, 3. So to 3, this would be 3.61 times 10 to the negative fifth. All right. Questions on this one? The only way you get good at this is doing lots of them. Practice, practice, practice. Do the ones in math and chemistry. Do the sum of. If you get stuck on something, try one out of the book that has the answer to see if you're on the right track. If you're not matching up, that says, "Oh, I'm making some type of error there."
We treat Ka just like the equilibrium constant.
Absolutely. Ka is an equilibrium constant. We just got a fancy name for it because when you start saying equilibrium constant, you want to tell the person what kind of equilibrium constant are you talking about. When you say Ka, or the acid ionization constant, what it tells a chemist is that the hydronium ion, or the hydrogen ion, either way you want to think of it, is in the expression. That's the key right there. Anytime somebody says Ka, they are talking about the hydrogen ion being in the expression. That's why we say Ka, not just equilibrium constant. Because why do we want to know that? Why do we want to know about the hydrogen ion? The hydrogen ion determines how strong of an acid we have. It determines the chemical properties of that substance. One of the big questions here with acid is most of the acids generated in the United States along the Gulf Coast and Texas. But then most of the acids are used to make plastics for like automobile dashes and things like that. How do we get the acid from Texas to Michigan or wherever they produce the plastics? Well, you say, well, we put it in on the railroad. What kind of car would you put it in on the railroad? What kind of car? It'd be a tanker, right? What's a tanker made out of? It's made out of metal. Acids are corrosive to metal. So how do we transport sulfuric acid, which would eat a metal up, from Texas to Michigan? You could have it glass lined. You could. That's a possibility. But most of the time, I'm not positive that some of them can be. Some of them could be glass lined, but there's another thing you can exploit here. And what would that be? When does an acid have the properties of an acid? When it releases, when it reacts with water and you form the hydronium ion. So if you put 100% sulfuric acid in the tanker and seal it, and it can't get any moisture to it, it can't form the hydronium ion to attack the metal. So that's what we do. We ship it at 100% pure, pretty close, 98, 99%. And then we take it out, and it's evacuated. It never comes in contact with the air to the plant to make the plastic. So you can't have the properties of an acid until it ionizes, till you form that hydrogen ion. So that's what we do. Now, what's the problem with that? If the rail car wrecks out here at Waller Avenue, what happens? That's right. We start pulling moisture from the air. All this humidity that's in our air that we breathe starts going right into the sulfuric acid. It's an exothermic reaction. It makes a big cloud of strong concentrated sulfuric acid. And if the winds are blowing this way, easterly, then they're laying right on us, right? So that's a big concern. It's always a big concern when we're transporting. And you see that. You see it on the news. Tanker crashes. Everybody in town has to be evacuated. Eats the paint off the cars, the houses, and everything. Most people get out in time because it's pretty dense cloud and it takes a pretty good wind to move it. But I mean, we would have, I don't know, it depends on what the winds are. We'd have to evacuate fairly quickly. All right? So remember that the acid has to ionize to give us those properties. All right? Let's do another problem. This one a little more complex. This is kind of where Nick's getting to. If you look at problem 77. So on problem 77, they want you to find the pH of a solution that contains a strong acid, like hydrobromic acid, and we're going to combine that with a weak acid, 0.125 molar HCHO2. Now tell me what that acid is. That's right, formic. So instead of saying HCHO2, you need to know the names of your acids, formic acid. Those of you in biology, formic acid is important. It's one of those substances that ants excrete to, fire ant excretes to give you that bite. So it's a formic acid, common substance in biology. All right, so hydrobromic acid, strong acid, formic acid, weak acid. Oh, let's do one more question. What kind of acid is hydrobromic acid? Binary or oxyacid? Binary. What's formic acid? Oxyacid. All right, because there's some oxygen in there. All right, so which one's the weak acid? Formic. So let's write the equation for formic acid. HCHO2. When it ionizes, what are my two products? All right. The hydrogen ion. Is there a charge on this ion? Has to be negative. Can't have excess of charge on one side of the yield sign. All right. What's the name of this ion? I ate something icky.
Oh, what time?
This ion that I've got underlined here. What'd you say? Form 8. Form 8 is correct. That's why we know we've got to memorize I ate something icky. You know it's formic acid. You know it's an oxyacid. So the conjugate base is the form 8 ion. That's why I remember I ate something icky. If the acid ends in ick, it's oxyacid, and that means the ion ends in 8. All right, so let's talk about initial concentrations. We're going to do an ice table here. What's the initial concentration of the formic acid? 0.125 molar. What's the initial concentration of the hydrogen ion? Oh, is it? Is it 0 or is it something else? What is it? No. What do we know about the hydrobromic acid? Strong acid, weak acid? It's a strong acid, so it goes 100% ionized. So that tells us the hydrogen ion concentration is what? Yeah, 0.115. Yeah, or 0. Yeah, either way you want to say it. 0.115. All right? See, that's why this problem's a little trickier. We start off with, you have taken a strong acid and a weak acid, you've poured them into a beaker, and we want to know what the pH of that solution is, and you've got to say, okay, the weak acid is what we've got to focus on, because the strong acid we know goes 100% to completion, 100% ionized, and that's how we know initially that the hydrogen ion concentration is 0.115 molar.
So we're not going to put
Those hydrogen are coming from the hydrobromic that already ionized.
That's right. I mean, you know, if you struggle on something like this, just draw a picture. Just draw like a beaker and say, okay, I know that hydrobromic acid completely ionizes, so there's my hydrogen ions, and then you also have the formic acid. Some of it is not ionized because it's a weak acid, and then some of it does, and that's what we're going to focus on, is that converting over to the hydrogen ion and the formate ion. But initially, right at the very beginning of the reaction, what we have present is the bromide ion and the hydrogen ion and the weak acid. All right, so what's the initial concentration of the formate ion? What's the initial concentration of this? 0. All right. All right, the next question is how much... Okay, so here's where Q comes really important. On any type where we're starting with product to begin with, we're starting with one of the products, you better think about Q. Slow down and think about what Q is. What's Q going to be for this reaction? Well, tell me what the value of Q is going to be. You should be able to tell me what the value of Q is going to be. Q is going to be equal to 0. The only reason why this one makes it easier is because, yeah, we still have a substance that's 0 on the product side. So it is 0, so Q is less than K. So which way is this reaction going to go? To the right, to the products. Why is that so important? Because when you go talking about change here, are we going to be gaining or losing formic acid? Losing. You said it went this way, so we're going to lose X amount of this, we're going to gain X amount of this, and we're going to gain X amount of that. That's why Q is so important. Q tells you what direction the reaction is going to go to reach the equilibrium constant. And if you don't get this right, then the rest of the reaction is wrong. And sometimes, like if they would have gave us some formate ion to begin with this, maybe the reaction is going reverse. And you would have had plus X for the formic acid and minus X for the two products. So you got to be careful. Yeah.
We didn't have K to compare Q to, though. Instead, you use it to compare Q to.
Well, but you know if Q is equal to 0, Q is always less than K. All right? So equilibrium, this is 0.125 molar minus X. This is 0.115 molar plus X, and this is plus X. We've got to put this in the expression. Ka equals the products, 0.115 molar plus X times X divided by 0.125 molar minus X. All right, right now we have two unknowns in this equation. We've got X is an unknown and Ka is an unknown. Can't have two unknowns in one equation. So one of these unknowns has to be known. Which one is going to have to be known? The what? The Ka, that's right. Because if we knew what X was, we wouldn't have to do this, right? So Ka has to be known. So where do we find Ka? From the table, that's right, from the table. So you go back flipping in your book. Let's go find what Ka is for formic acid. That's why you got to know the names of these acids. They're being a little nice to you in this book because they do give you the chemical formula for it as well. But when you're looking at tables in a handbook, they generally don't always give you the formula. All right, so what is it? All right, 1 point. You don't have to memorize them, no. You just have to know you have to go find them. And they can either be in the problem or they can be in a table in the test. But you don't have to memorize them. No, nobody would memorize. Although I would say by the time we get through chapter 16, you will have acetic acid memorized because it comes up so often. All right? So now what are you going to do? You're going to solve for x and go, oh, do I have to do a quadratic? Well, here's my rule of thumb, right? If it's 10 to the fourth difference, we probably don't have to do the quadratic. This is close because this is 1 times 10 to the negative 1, so it's more like 10 to the third. But who wants to do the quadratic? So let's first try it by saying these two x's are negligible. All right? Yeah, both of these. This x is negligible and this x is negligible compared to the original concentrations. All right? Now, x by itself is never negligible because that's a change. You had 0 and now you got some. But the other two, you've got concentrations initially, and maybe that change in x isn't going to be that much. So let's try it out and see. So this is the best you can do at this point. Try it out and see. Oh my gosh. Oh, well, no wonder the thing unplugged. All right.
Why did you get rid of the x in the numerator?
I got rid of the x in the numerator with the hydrogen ion. I'm assuming that 0.115 is much greater than whatever the change in x is going to be. And I got rid of this x here because I'm assuming 0.125 is a much greater concentration than the amount of x I'm going to lose here. Now that makes it easy, right? All I have to do now is take this number, multiply it by this, and divide by this, and that will solve for x. So let's do that and see what we get for a... it's not like that. See, that's what I see a lot of students think it always is only in the denominator or something like that. The reason why we can say these x's are negligible is we are saying the amount of change in this x or this x is negligible compared to the original concentration. So we can do that for whatever's in the numerator or denominator. We're assuming these x's, these changes, are negligible compared to the initial concentrations. Now, the other x, again, this x cannot be negligible because there's nothing to compare it to. It was 0 to begin with. So it's important that x is important. All right, so let's figure this out and see what happens. We get 1.8 exponential negative 4. We multiply that by 0.125, and we're going to divide that by 0.115, and we get 1.957 times 10 to the negative 4. Is that what you guys are getting? All right, so what are you going to do now to see if this assumption was right that those x's are negligible? All right, you're right. James is right. So now we got x here. This is the amount of change. We're going to take the amount of change, divide it by the original concentration here, multiply by 100, and see what that percentage is. If it is less than 5%, great assumption. If it's 5% or more, then we have to go back and do the quadratic. That's why I brought this other calculator. You guys can take this TI-83 and get online. You can program this calculator to just put in A, B, and the coefficients, and it will give you the roots. So you can Google that. Google quadratic for TI-83, and they'll tell you how to punch it in. That way you don't have to do the quadratic and punch. I don't have any problem with you doing that on the test. I'm not here to teach you a math class. It's about chemistry. So if you want to program your calculator to put in the coefficients and it spits out the roots for you, that's fine. All right? So when we take x and we divide it by 0.125, multiply by 100, what do we get? 1.56? 0.156, all right. So that tells us what? We're good. That's right. That this is fine. Okay. So what are we going to do with that number? Yeah. This is where I see some students.
Is that the number you got?
X, yeah. For X? You're not getting that?
No, I got 1.28 up to the negative 4.
All right. Well, let's recheck our work then.
I did,
Yeah, I'm just saying that the percentage.
I did 1.8 up to the negative 4 times 0.125,
divided by 0.115. Yeah, and I get 1.956 times 10 to the negative 4. All right. Well, let's go on because we've got 5 minutes here. I want to make sure we can do this part and we'll come back. All right, so this is another big mistake I see with students. A lot of times on multiple choice tests, this will be one of your answers on multiple choice tests. And they'll say, there's my answer. But that's not the answer. The question is, what is the pH? In order to find the pH, you have to know what the hydrogen ion concentration is in equilibrium. So you have to take this number, go back up to your ICE table, and take 0.115 and add to it the value you got for X. All right? So we're going to take 0.115 and we're going to add it to this 9.57. All right, so we get 0.1152. Notice it really didn't make that big of a difference, did it? And the 3 significant figures there didn't make any difference. All right, but you're going to take the negative log of that number. This is the hydrogen ion concentration at equilibrium. To find the pH, you're going to take the negative log of 0.1152 or whatever digits you have on your calculator if you haven't rounded it off. I usually just carry it all at this point. And then take the negative log of that. And you get a pH of what? 0.938. 0.938. How many significant figures? 3. All right. So there's my 3. 0.938. All right, so is this solution acidic or basic? Highly acidic. It's almost a pH of 1 or 0, somewhere in that range. Really low pH means really high acidity. Does that make sense? Yeah, because you had 0.115 molar strong acid in this solution. That's what's dominating. In fact, really, look how much the formic acid contributed to the hydrogen ion concentration. Not much. 10 to the negative 4. So, some of you might be saying, well, why did we do all this? Why don't we just take the negative log of the hydrogen ion concentration? You could. The 2 significant figures, you would have got the same answer, right?
Did we not do anything in the HBO because ion is fluid?
Yeah, where we worked with the hydrobromic acid was, that's what gave us this number initially, right? Right here. Other than that, we don't have to fool with it. Yeah.
We could have really seen the Ka for formic acid is 1.8 times 10 to the 4 compared to 1.25 is significant difference. So the negative log of 0.115.
Yeah, you could have said this. You know the hydrobromic acid's Ka is much, much greater than formic acid's. So formic acid is not going to contribute significantly to the pH. But into 3 significant figures, no, pretty much doesn't. Maybe that last digit it does, but you don't know that. You guys got to work that out. I mean, at some point you get the handle. Like, what I want you to get out of this is you should know that this sounds like a reasonable answer for this problem because we started out with a strong acid. And so we should expect a low pH. All right, we'll stop here. And like I said, on Monday, I'm going to talk about salts and how we know what molecular structures make a strong acid, weak acid. And we'll probably talk about Lewis acids and bases. We'll wrap up chapter 15 on Monday. So you should get caught up. These are some problems to help you do your master in chemistry. Get caught up and get ready to take the test next Wednesday. All right?
Can you use the formulas that we learned in chapter 14 or on the chapter?
You may. I'll tell you where you may.